Ladies and gentlemen, welcome back to the channel. How are we doing today? So today I wanted to make a video on induction motors and I wanted to talk about specifically something called slip and how slip relates to current and torque. When I was new in the HVAC trade, I had a couple of times I misdiagnosed things with motors because they have some odd behaviors that you don't really expect. One of the things I've noticed with these motors is that when you increase the resistance in series with the motor, so let's say you have a loose connection that's heating up and it's getting burned up, and that's additional resistance that's developing in series with the windings of this motor. And if you think about that from a purely Ohm's law perspective, it doesn't really make sense because if you add resistance to a circuit, all of the things being equal, the current should fall. It shouldn't increase. But induction motors, the current does increase when you get a burnt connection, even to the point where it can trip the breaker. So I had this compressor one time that was tripping the breaker, and I was kind of green, so I didn't do all of the rigorous, practices you're supposed to do before you condemn one. And I just yeeted a new compressor in there and found that the new one also tripped the breaker. And so I eventually found that burnt connection, repaired it, and to my knowledge, that compressor is still running to this day. But that's a very expensive mistake, and it really hurts your reputation. So, if I can help one of you guys, just one of you guys, not make a mistake of that magnitude, that makes making this video worth it to me. I've wanted to make this video for quite some time now, but I, I felt that it was a video that I shouldn't make until I had some sort of animation to make things visual for you guys. Induction motors, it's really hard to just ramble about these things without a visual and have it make sense. So I figured, having this model that I've made here would help improve the clarity of this video, and maybe you'll walk away from this with a better understanding of slip and how it influences current and all those different things after watching this video. So, yeah, thank you for tuning in. I appreciate it. And I worked very hard on this thing. I hope you guys enjoy it and I hope you get some benefit out of it. But yeah, let's get started. Yeah, so this is your typical three-phase industrial induction motor. And these things are ubiquitous. They are everywhere, used in all sorts of different industries. You see them in CNC machines, HVAC systems, you name it, they're in it. So pays dividends to learn about these things. Right here we have the chassis. Normally it's painted blue. Sometimes they can be different colors, but seems like the Baldor Alliance motors are typically blue. Um, and you have the shaft right here. So this is the business end that does all the heavy lifting, and it rotates whatever you're wanting to rotate. And you have this little hoist right here, and I definitely recommend using these if you have a large motor because these things are really heavy. So you can hook a come along to them or a chain or something or a hoist and put them in place, so you're not you know injuring your back and stuff. And all the way back here, usually there's a fan that attaches to this side of the shaft that helps pull air, either pull air or push air through these vent holes. And that air gets forced across these little rib sections right here. And these little rib sections increase the surface area so the motor can dissipate heat more effectively. So we all know that motors don't like heat, and a good way to increase the longevity of a motor is to decrease its operating temperature, right? And so that's the thinking behind these little ribs right here. So then we got the electrical section right here, and back here behind the electrical section we've got Daryl Wood chilling out right here. Sometimes it's just obvious that an electrician's been in here at some point. So we'll just take this out. And then behind there, we got this terminal block. And so this is a three-phase motor. So it has three dedicated phases, three separate windings, right? And each of those windings has two ends. And each of those ends will go to one of these terminal blocks. And so having six terminals right here allows you the freedom that you can run this motor in either star or delta, or you can run a star delta starter on it if you wanted to. Generally star has a lot less inrush current, so it's nice to be able to start a motor in star, but then switch it into delta once it reaches its terminal speed. You see that a lot, but yeah. So that's pretty much the chassis. The next thing we're going to talk about is the stator and rotor assemblies. All right. Here's the model of the stator and the rotor. And yeah, you can see the rotor's in the middle here. Obviously, rotor means rotate and stator means stationary. So let's take the rotor out and just talk about the stator for right now. So the stator, if you notice, it's got this core material. It's laminated just like a transformer, and it's laminated for the same reason, to break up the crystalline structure to prevent these small eddy currents that can develop within those crystalline structures, and you can end up canceling the fields out somewhat, and it can make the motor not perform as well as it could, and you can get localized heating in those areas as well. So that's why it's laminated, just the same exact reason as a transformer or any other um, magnetic device like that. So this is a three-phase motor, like I said. So we've got three identical coils around the perimeter of the stator, and they are offset radially around the stator by 120 degrees apiece. All right. And so remember, there are phases U, V, and W. If we take phase U out, then we're left with just these two. So that winding is gone now. And you can see we're taking up 5 slots here and then 5 slots down here. And what that tells you is that this motor is a two-pole design. All right. And when it comes to motors and poles, there's a lot of confusion around that, but I'm going to put up an equation that shows you the relationship between the rotational speed of the motor, or the synchronous speed of the motor, versus the number of poles that you have. All right. And so the lower the number of poles, the greater the rotational speed will be, but it comes at the cost of torque. You're sacrificing torque to gain rotational speed, which sometimes that's what you want, but it's not what you always want. So if you want a really stout and strong motor that has a ton of torque, you want to opt for one that has more poles rather than less, right? And so here, I'll show you this. So that's what a single winding looks like. So you've got a winding pitch of 15. So this coil goes from this to here, and then that winding goes from there to there. But they're all together in parallel with one another, and they're on the same phase. So if we take the core and the liners out, this is what that individual winding would look like, and then all three of them together work in conjunction to create a rotating magnetic field. And I'll show you that here in a second. But let's talk about the rotor next. All right, so here is the rotor and the stator, and I took away the pretty background because it was messing with the rendering a little bit. But you can see there's this small air gap between the two. And the bearing is, or I mean, the rotor is suspended by bearings on each side, so it sits constantly in the very center of this stator. And that is critical, to a good motor design. You don't want that because you'll get wobble, so they take great care to make sure that the bearings are centered properly on these. So let's take this stator away and we'll just look at the rotor itself. Once again, it's laminated for the same reason. But what I want to stress here with this rotor is that it is not magnetic in the slightest, right? It's not a permanent magnet at all. And so if you look at this rotor, you have these two things right here. So these light sections on the ends are called end rings, and they are solid, so they go all the way out and they extend beyond this, and it's basically a solid piece of conductive metal. All right. And then you have these bars. Now these bars connect these two end rings, and they short each side of these end rings out together. And notice that we have these rotor bars are not straight completely. These are skewed, and that helps with the stability of the motor. It helps reduce the effect of something called cogging, where cogging is where the motor would want to get stuck. It would have more magnetic resistance at one point in the rotation than others, and you end up with it's not a smooth turn around the perimeter of the stator. You have spots that where it wants to stick more than others, if that makes sense. So this helps mitigate that. And these bars, like I said, they're also conductive. That is highly important that we understand that. Anything that is a lighter shade here is conductive. Anything that is darker is not electrically conductive, but it has a low magnetic reluctance, right? And so it's very easy for flux to course through this material relative to the air that's around it. All right. And so that's pretty much our rotor right there. And it connects to the shaft. And like I said, there's a bearing on the front and a bearing on the back that provides stability. And yeah, so that's pretty much your rotor right there. And let's talk about our rotating magnetic fields next. That's the part I really want to get to. That's the cool part that I'm really proud of. So I'm really hyped to show you this part. So yeah, we've got our stator dead on here, and let's talk about these fields now. So since this is a three-phase motor, we've got three individual coils that have their own magnetic field, their own dedicated field, and they're 120 degrees offset, just like the coils are 120 degrees apart around the stator. And that ends up creating this rotating magnetic field. So you can see the North Pole is traveling along the periphery of the stator, and it's rotating. Now, make note here is you can see my frame markers down here. So this is frame 1 that I'm on, and now I'm on frame 0. All right. Now, what I want to stress here is that I made basically the frequency 120 frames here. So if I start on frame 0, notice we've got this configuration of our field. The blue is on the right and the red is on the left. If I go to 120, we end up at that same exact configuration. So this is one complete AC cycle right here. And so that tells you that, once again, this is a two-pole motor because it takes one full AC cycle to create one revolution of this magnetic field. And if we do it halfway, if we go to frame 60 right here, we have, our magnetic field is inverted. So that tells us that we're halfway through the cycle. Now, the beautiful thing about this is if we go back to frame 0 again, the sum of these fields ends up creating its own field. So these fields are influencing one another and they're summing together. And when you sum these fields together, you end up with one main stator field that's going to be this white field right here. Now notice it is completely aligned with these magnetic fields. It's completely horizontal right now because of the way that these magnetic fields are, the way that they are in this current moment. And watch this. This is pretty cool. So when one of them peaks, like this one peaks right here, that means that this field right here is dominating it. And these other two fields, since they are equal in magnitude and they are aligned, the way that they're aligned, they basically cancel one another out and they don't really influence the final field all that much. All right. And if we keep going down these 10 frame intervals, now look at this. So now they are aligned this way. And so our field is going to be, it's going to have this orientation in this moment. We go another one, we'll hit another peak right here. So now we're hitting the vertical peak right here. And once again, these two are canceling out again. But just look at how elegant this is. I mean, this three-phase motor was invented in the 1890s. I mean, it's just incredible to me that something this elegant was made that far back in the past. It just blows my mind, honestly. It's revolutionized industry forever when this thing was invented. But yeah, I just wanted to show you guys that. And keep in mind, if this happened to be a four-pole motor, this we wouldn't return back to this configuration that we hit until we hit frame 240. With a four-pole motor, it takes two full AC cycles to make one revolution happen with a four-pole motor. Whereas a two-pole motor like this one, once you hit 120 frames, we are back where we started again. All right. So yeah, that's our rotating magnetic field. And next, let's talk about how this interacts with the rotor to actually create mechanical work. That is the most critical part of understanding these. And this is going to bring me back to the beginning of this video when I was talking about why bad connections cause these things to draw heavier current. It's going to make sense in the end, I promise. All right, so here we have our stator and our rotating fields and our rotor rotating simultaneously all at the same time. And yeah, so let's go ahead. I'm going to take away these three fields and only focus on the one. I'm also going to take away the stator core here. And I want you to watch this rotor rotate relative to the field and see what you notice. Let's take a look at this up close. Let's slow it down and take a look. All right, so this arrow, just kind of ignore it for now. Just kind of watch the field relative to the rotor and see what you think happens. So the field is obviously rotating faster than the rotor is, right? And that is the critical thing that makes induction motors work. All right. So that difference in speed in percentage is called slip. All right. So there has to be slip for an induction motor to generate torque. All right. So let's think about this for a second. So we have these conductive bars here, and they're shorted between these two end rings on either end. And what happens to a conductor when you have a change in flux? You know, when there's flux cutting across it, what happens to that conductor? You're exactly right. It has current induced into it. Actually, it has EMF induced into it first. But since these rotor bars are just dead shorts all the way around, that EMF immediately turns into induced current. And so that induced current, what happens when you get current? You get another magnetic field that opposes the one that created it. All right. And that is the mechanism that allows this motor to work. So we're relying on the slip to magnetize the rotor for us. Okay. So what I want you to see is this yellow arrow right here. It represents the induced current in this specific rotor bar. Now keep in mind this arrow, this process is happening completely on all of these bars are having currents induced into them at specific times. But what I want you to notice is how this current in this specific bar changes over time with the position of this field. Now remember, it's change in flux that dictates the amount of current. The more change in flux you have, the more current you will induce. All right. But the thing is that on this magnetic field, the flux is not uniform throughout this entire field. The flux paths are more concentrated in the center of this field than they are on the outside of this field. So if we zoom back in here and we watch our stator field outpace the rotor, watch what happens to this current as the center of this field gets nearer to that specific bar. All right, the current gets larger, it grows, and in fact, it peaks at this very moment. All right. This is the moment where, d phi over dt is at its greatest point. And likewise, this bottom bar will also be experiencing the maximum d phi over dt. So that is when you have the highest amount of change in flux, and these two bars will have the most current. And then this will have the next amount of current, the next most amount of current, so on and so forth as you make it all the way across. And then these that are, 90 degrees away will have, the least change in flux. All right. And so that is the way that these induction motors work. So we're relying on this induced current to create a counter magnetic field that attracts the rotor to the stator and allows it to develop torque and rotate. All right. So now I think we're ready to do some thought experiments and think about some different scenarios that can arise with these motors and see if we can predict what would happen. And this is going to lead us to answer the question at the beginning of my video. So what I'm going to do is this is my rotor right here. And what I'm going to do is I'm going to take this rotation away and just make this 0 degrees. The rotor will just be completely stationary. So this would be like a locked rotor condition. All right, so there's something locking our rotor that is, the motor doesn't have enough torque to actually overcome it. So the rotor just sits here stationary. Well, what happens to our change in flux? It goes bonkers. It goes through the roof, and so does our current. And that's why we have locked rotor amperage as one of the statistics on the data plate of a motor. And so that's when you get your highest absolute current is when the rotor is completely stationary. Okay. And next thing I want to think about is inrush current. All right. Where does inrush current come from and why does it happen? Well, it happens because this rotor is stationary when that contactor first pulls in 99% of cases. So when the contactor pulls in, this rotor is completely stationary. But if we think about this synchronous field, the stator field, it's the synchronous speed, and the synchronous speed never changes. So if this is a two-pole 60 hertz motor, it's going to have a synchronous speed of 3600 RPM. And so that means as soon as this contactor pulls in and the stator windings get energized, they are going to be turning at 3600 RPM that same instant. All right, there's no ramp up time, it's going to be instant. And so this rotor is stationary for those first few moments. It's going to start turning, but it's turning very slowly at first. And especially if you have, a very high mechanical load on this, that just compounds it and makes it stay in that slow rotation for longer. And so, your slip, when the motor starts, your slip is like really, really high. And then as the motor kind of warms up and gets sped up, the slip decreases. And then eventually you'll hit like a steady state. But that's where inrush current really comes from with these motors. And yeah, let's talk about, why bad connections cause the motor to draw heavier current. Because that's really a mind bender when we start thinking about that. Yeah, so now let's think about what happens if we have a bad connection. So, we have our rotor rotating right here. But let's imagine that we have, bad connections on all three phases that are equal in severity. Or even better, let's just imagine that the wiring is undersized on the way to this motor. And so we have a voltage drop, right? Anytime you have, a bad connection or undersized wire, it's going to heat up. And anytime you're using electrical energy to heat something up, you're going to have a drop in voltage. You're loading it down. And so that means that the effective voltage seen by this motor, by the stator windings, is going to be less than it's designed for. And, what dictates the size of the magnetic field? Well, the magnetic field size is dictated by the amount of current through the stator windings. But if the voltage drops to the stator windings, then that means that there's going to be less current traveling through them, and our magnetic fields will be smaller than they used to be. So now these are a lot weaker. Okay? So, how is our rotor going to react to this? Well, if our stator field is weaker, that means that we're going to have less flux. If we have less flux, we're going to have less current in the rotor. Now, this is all going to be temporary. We're thinking about the state of things as they develop, right? This isn't what happens in the end, but for right now, we have less rotor current. All right. And that means that the entire magnetic fields in this motor will be reduced, they'll be less strong. It's what happens if that happens. If our magnetic fields are less strong, we get a reduction in torque, and we can assume that our mechanical load is going to be the same. It's going to be constant and not changing very much. And so that means that our rotor has no choice but to slow down. Okay? But think about it. What happens to our rotor if it slows down? What happens on locked rotor conditions? We get an increase in rotor current and also stator current. The rotor currents somewhat reflect back onto the stator again. It's just like a transformer. When you load down the secondary, the primary fills it. The secondary impedance gets reflected back onto the primary. And that's why the primary can also be damaged if you short the secondary of a transformer. And so, even though these fields are weaker now, our rotor is a lot slower. Our slip has increased, which means that the rotor will be robbing more current from the stator. And thus, the stator will also draw heavier current. And the sad thing is with this is that, if you have a burnt connection, it creates a positive feedback loop. The burnt connection will heat up more and it gets worse. And then the motor responds by drawing more current from it. And then the burnt connection gets even worse. And it becomes this loop where it eventually destroys the connection entirely and the wire breaks down enough that it can no longer conduct. And if that happens on one leg on a three-phase motor, yeah, it can still work sometimes, but it's going to be single phasing. You're going to put more stress on these other windings, and it's just not good at all. Single phasing a three-phase motor is not good. It might work, it might start up sometimes, but you're really harming the motor. And so hopefully that helped you guys understand these things. It took me a while to get to the bottom of why this happened, but eventually did. And I felt like it was something I needed to share because I don't really hear people talk about motors from this perspective all that often. So I felt like the world needed it. And like I said, if this helps one of you guys not make the mistake of changing, a compressor that's not bad, that makes it all worth it to me. It's really embarrassing when you make those mistakes, and it really hurts your reputation, and it causes people to lose trust in you. And so, I felt like I had a duty to share this with you guys. But yeah, thank you very much for watching and tuning in. I hope you enjoyed this animation. I really enjoyed making it. It was a lot of hard work, but it paid off in the end, I think, because there's definitely a void in good motor animations out there, and I was really proud at how this turned out. So yeah, if you want to see more videos like this, feel free, like, share, subscribe, give me some love, and yeah, I'll continue making these videos. I do plan on making more videos in the future that are physical, where I'm actually troubleshooting stuff and walking you guys through how to work on different things. But my house got flooded out in Helene, and I'm not living there right now, and I lost my lab and a lot of my stuff in the storm, and so we're trying to rebuild from that. But yeah, I appreciate y'all watching. Take care.